Ladies and gentlemen, welcome to this lecture on direct current charging or DC charging of electric vehicles. In this lecture, we are going to learn about three things. First, what are the key parts of a DC charger? Second, what types of connectors are used for DC charging? And third, what are the limitations of DC fast charging? First of all, let's have a look at what are the key parts of a DC charger. DC fast chargers typically operate at level 3 charging powers and are designed to charge electric vehicles quickly with an electric output ranging between 50 kilowatts to 350 kilowatts. With higher power operation, the AC to DC converter, the DC to DC converter, and the power control circuits become larger and more expensive. This is why DC fast chargers are implemented as off-post chargers rather than as on-board chargers, so that it does not take up space within the vehicle and the fast charger can be shared by many users. Let us now analyze the power flow for DC charging from the DC charger to the electric vehicle battery. In the first step, the alternating current or AC power provided by the AC grid is first converted into direct current or DC power using a rectifier inside the DC charging station. Then, the power control unit appropriately adjusts the voltage and current of a DC converter to control the variable DC power delivered to charge the battery. There are safety interlocks and protection circuits used to de-energize the EV connector and to stop the charging process whenever there is a fault condition or an improper connection between the EV and the charger. The battery management system, or the BMS, plays the key role of communicating between the charging station and to control the voltage and current delivered to the battery and to operate the protection circuits in case of an unsafe situation. For example, control area network, shortly referred to as CAN, or power line communication, shortly referred to as PLC, are used for communication between the EV and the charger. Now that you have a basic idea of how a DC charger is configured, then let us look at the main DC charger connector types. There are 5 types of DC charging connectors used globally. First is the CCS, or the combined charging system, called the Combo 1 connector, which is mainly used in the US. The second is the CCS Combo 2 connector, which is mainly used in Europe. The third is a CHAdeMO connector used globally for cars built by Japanese manufacturers predominantly. Fourth, the Tesla DC connector, which are used for AC charging as well. And finally, China has their own DC connector based on the Chinese GBT standard. Let us now look at these connectors one by one. The combined charging system, or CCS connectors, also referred to as combo, are integrated connectors for both AC and DC charging. They are derived from type 1 and type 2 connectors for AC charging by adding 2 extra pins at the bottom for high current DC charging. The connectors derived from type 1 and type 2 are respectively called as Combo 1 and Combo 2. Let us first look at the CCS Combo 1 connector. In this slide, the Combo 1 vehicle connector is shown on the left side and the vehicle inlet is shown on the right side. The vehicle connector of Combo 1 is derived from the AC type 1 connector and retains the earth pin and the tool signal pins, namely the control pilot and the proximity pilot. In addition, 2 DC power pins are added for fast charging at the bottom of the connector. On the vehicle inlet, the pin configuration, the upper part is the same as the AC type 1 connector for AC charging, while the bottom 2 pins are used for DC charging. Similarly, the CCS Combo 2 connectors are derived from the AC type 2 connectors and retain the earth pin and the 2 signal pins, namely the control pilot and the proximity pilot. 2 DC power pins are added at the bottom of the connector for high power DC charging. Similarly, on the vehicle inlet side, the upper part facilitates the AC charging from 3-phase AC, and at the bottom part you have the DC charging. Unlike Type 1 and Type 2 connectors that uses only pulse width modulation or PWM signaling on the control pilot, the power line communication or PLC is used both in the Combo 1 and Combo 2 chargers, and this is produced on the control pilot. Power line communication is a technology that carries data for communication on existing power lines used for simultaneous transfer of both signal and power transmission. The CCS combo chargers can deliver up to 350 amps at a voltage between 200 to 1000 volts, giving a maximum output power of 350 kilowatts. It must be kept in mind that these values are continuously updated by the charging standards to cater to voltage and power requirements of new electric cars. The third DC charger type is the CHAdeMO connector, which is a Type 4 EV connector. It has 3 power pins and 6 signal pins for its operation. The CHAdeMO uses the Control Area Network or CAN protocol in the communication pins for communication between the charger and the car. A Control Area Network communication is a robust vehicle communication standard designed to allow microcontrollers and devices to communicate with each other in real time without a host computer. As of now, the voltage and current and power levels of the CHAdeMO are ranging from 50 to 500 volts with a current up to 400 amps, thus providing a peak power of up to 200 kilowatts for charging. In the future, it is expected that EV charging up to 1000 volts and 400 kilowatts will be facilitated by CHAdeMO. Now let's move on to Tesla charger connectors. The Tesla supercharger network in the United States uses their own proprietary charger connector, while the European variant uses the Type 2 Mennekes connector but with DC charging built in. The unique aspect of Tesla connector is that the same connector can be used for both AC charging and DC charging. Tesla now offers DC charging up to 120 kilowatts, and this is expected to increase in the future. Finally, China has their own DC charging standard and connector that uses CAN bus, Control Area Network bus, for communication. It has 5 power pins, 2 for DC power and 2 for low voltage auxiliary power transfer and 1 for ground, and it has 4 signal pins, 2 for the proximity pilot and 2 for the Control Area Network communication. As of now, the nominal voltage used for this connector are 750 volts or 1000 volts, and the current up to 250 amps is supported by this charger. As you can already see, fast charging is quite attractive because of the very high charging powers going all the way up to 300 or 400 kilowatts. This results in very short charging times. But fast charging power cannot be increased infinitely. This is due to 3 technical limitations of fast charging. Let us now look at these limitations. First of all, high current charging leads to high overall losses both in the charger and in the battery. For example, if the internal resistance of a battery is R and the losses in the battery can be expressed simply using the formula I squared R, where I is the charging current, then you will notice that the losses increase by a factor of 4 times whenever the current is doubled. Secondly, the second limitation is coming from the battery. When fast charging a battery, the state of charge of the battery can only be going up to a state of charge of 70 to 80%. This is because fast charging creates a lag between the voltage and state of charge, and this phenomenon increases as the battery is being charged faster. Hence, fast charging is typically done in the constant current or CC region of the battery charging, and after that the charging power is reduced gradually in the constant voltage or CV charging region. Moreover, the battery's charging rate or the C rate increases with fast charging, and this then leads to reduction in the battery lifetime. The third limitation is coming from the charging cable. For any EV charger, it is important that the cable is flexible and lightweight so that people can carry the cable and connect it to the car. With higher charging powers, thicker and thicker cables are needed to allow more charging current, else it will heat up due to the losses. DC fast charging systems today can already transmit charging currents up to 250 amperes without cooling. However, in the future with currents above 250 amperes, the charging cables would become too heavy and less flexible for usage. The solution would then be to use thinner cables for the given current with cooling systems built in and thermal management to ensure that the cables don't heat up. This is of course more complex and costly than using a cable without cooling. So, to wrap up this lecture, in this lecture we saw the key parts of a DC or a direct current charger. Further, we looked at the different types of DC connector types. Finally, we analyzed the various limitations of DC fast charging. Thank you for your attention.